Hey students, today we're looking at our final activity for this priority standard, Standard 2C, and that is on quadratic transformations. So we've spent the first 5 lessons of this standard just focusing on transformations in general and really breaking them down. And we applied them to absolute value functions, linear functions, some quadratic functions, and now we're going to specifically focus on quadratic transformations because that is what you're going to be tested on. So we're looking specifically at the basics of a quadratic formula, and if you remember, with our quadratic parent function, our parent function is y equals x squared. So if we want to transform our parent function, we can look at this a value here, and that's going to indicate a reflection over the x-axis if it's negative, and if it's a value that's larger than 1, it'll indicate a vertical stretch, and if it's a value between 0 and 1, it'll indicate a vertical shrink. We also have this h value here, and that indicates a shift left or right. If I am plugging in a positive h, that's going to be a shift to the right, and if I'm plugging in a negative h, that's going to be a shift to the left. But remember that that looks backwards from what we expect. So if you were to see something like y equals x plus 3 squared, that's actually a transformation left 3. And finally, we have this k value here, and that indicates a shift up or down, where if I have a positive k value, I'm shifting up, and if I have a negative k value, I'm shifting down. So for example, if I had an equation like y equals x squared minus 3, that would mean I'm moving down 3 from my parent function. So one of the questions on your test is going to ask you to identify what the a, h, and k values do to transform your graph from your parent function. So this is essentially what I'm asking for. I'm asking you to explain what a can do and what h can do and what k can do, and the more detail you can give me, the better. Here's just kind of a breakdown of our different translations. Horizontal translations, those are going left or right, and vertical translations are going up or down. And remember that the formal word is translation, but you can also say shift, and that means the same thing. So anytime that we're looking at this h value, just remember that if we plug in a negative h, that's going to shift to the left, and if we plug in a positive h, that's going to shift to the right. But once again, this is always going to look backwards from what we expect. Anytime we're messing with our input value, it should always look backwards from what we expect. Whereas with vertical shifts, it does not look backwards from what we expect. If we want to shift down, we're going to subtract a k value, and if we want to shift up, we're going to add a k value. So here is our first example. We want to describe the transformation of f of x equals x squared, our parent function, our parent quadratic function, represented by g of x equals x plus 4 squared minus 1. So the first thing I notice is that this plus 4 here, that's affecting my h value, and my h value shifts my graph left and right. So if I have a plus 4 in here, remember that's kind of backwards from what I expect to be, so that's going to represent a transformation or a translation left 4. And this minus 1 on the end, that's like my k value. So this minus 1 here is going to represent a shift down 4. So I can just look at this equation and identify those transformations, but let's say you're having a hard time doing that. You can always go back to a graphical representation. So if we graph our parent function, which is this guy right here, which I'm highlighting over in red, and we compare it to this new function g of x, which is in blue, we can see that to go from my parent function to my new function, I'm going down 1 and left 4. So when in doubt, graph it out. Alright, so hopefully by now you can just look at an equation and determine what transformation has occurred from the parent function. So looking at this equation, g of x equals x minus 3 squared, and I've given you the graph on the right here, what transformation has occurred from the parent function? Hopefully you were able to tell me that we've gone right 3. And if you're having trouble identifying that, just remember that this is on the inside, so if we're adding or subtracting something on the inside of our parentheses, that's changing the input value, so that's changing our x values, which moves it left and right. And anytime we're affecting our input value, it's backwards from what we expect, so a minus 3 actually means to the right, whereas a plus 3 would mean to the left. Or you can also go back to graphing. So if you think about our parent function, y equals x squared, if we were to graph that on here, we'd have 0, 0, we'd have 1, 1, we'd have 2, 4. So this would be that parent graph, and I can see that the transformation that's occurring here is just a shift to the right 3. Alright, try this one. What are the two transformations that are changing from our parent function? Well, hopefully you notice that this minus 2 is on the end here, so that's changing our output value. So this is going to represent a shift down 2, whereas this minus 2 is on the inside, so that's affecting our input values, or our x values, and therefore it's backwards from what we expect, so this is going to represent a shift right 2. So from our parent function, we've moved right 2 and down 2. And once again, you can graph that parent function to just kind of compare it to the original here, and you can see that the change that's occurring is I'm going down 2, right 2. Alright, try this one. Alright, in this case, this plus 1 means that we've gone up 1, and this plus 5 on the inside of our function means we've gone left 5. So from our parent function, we've moved left 5 and up 1. Alright, now we're going to take a look at reflections. Anytime we have a reflection over the x-axis, our x values stay the same, but our y values change. This means that I'm taking my y values and multiplying them by a negative. In other words, I'm using this rule of taking a negative times my function, or times my y value. If I'm doing a reflection in the y-axis, however, that does not change my y values, it changes my x values. So my y values stay the same, but my x values are opposite of each other. You'll notice that this graph looks like I don't have a reflection. That's because the y-axis is a line of symmetry for the parent function of a quadratic. So my reflection over the y-axis, what that's doing is it's changing my x values by multiplying them by a negative, so I'm using this rule, f of negative x, where my input value is being affected rather than my output value. We can also take a look at horizontal stretches and shrinks and vertical stretches and shrinks. So horizontal stretches and shrinks, these are affecting the x value, meaning that they're happening on the inside, or they're affecting my input values, and specifically I'm multiplying by some value a. And remember that horizontal stretches and shrinks are backwards from what we expect, specifically, we use the reciprocal of what we expect. So, for example, if I have a horizontal stretch by 3, the rule I would be using is f of 1/3 x. So it's the reciprocal of that description. With vertical stretches and shrinks, however, it's not the reciprocal value. I'm just using this rule, a times f of x, where I'm taking my y values or my output values and multiplying by some sort of value. So let's take a look at this example. We want to describe the transformation of f of x equals x squared, that's our parent function, represented by g. And then we want to graph each function just to make sure. So g is listed as negative 1/2 x squared. The first thing I notice is this negative here. This negative is on the outside of my function, so it's affecting my outputs. And I also notice this 1/2, which is also affecting my outputs. So the negative, that's going to be a reflection, and since it's on the outside, it's going to be a reflection over the x-axis. And this 1/2 is a vertical stretch or shrink, and in this case, since it's 1/2, it's going to be a shrink. So I can say a vertical shrink by 1/2. Then I graph both my functions just to see, and it looks like I do have a reflection over the x-axis, and it looks like my graph has been shrunk vertically, which makes my graph look wider than it did before. Alright, let's take a look at this example now. So once again, I'm starting with my parent function, and I'm determining what sort of transformations have occurred, given my new function. So the two pieces of this new function that's changed is this 2x, which notice that that's inside of my parentheses, so that's changing my input values, and also this plus 1, which is affecting my output values. It's on the outside of my parentheses. So this 2x here, that's going to be a horizontal stretch or shrink. And remember that when I talk about horizontal stretches and shrinks, they're backwards, or they're the reciprocal of what's inside of my function. So in this case, since inside of my function is a whole number 2, I'm going to say that this is actually representing a horizontal shrink by 1/2. Whereas this plus 1 is moving my graph up 1. Alright, your turn. Tell me what transformation is represented by this graph. Think about what's changed from our parent function. Alright, since this 1/3 x is inside of my squared term, or inside of my parentheses, it's affecting my input value. That means it's going to be a horizontal stretch or shrink. And remember that with horizontal stretches and shrinks, we do the reciprocal. So this is going to be a horizontal stretch by a factor of 3. Alright, try this one. In this case, we have two pieces of our equation that are being affected. We have this 3 here, which is outside of my squared term, so that's going to represent a vertical stretch by 3, because remember that with vertical stretches and shrinks, we don't do the reciprocal. And we have this negative 1 inside of our function, so that's affecting our input value, which means it's a left or right. Left or right is backwards from what we think, so this represents a right 1. So we have a vertical stretch by 3 and a shift right 1, and you can always graph the parent function and compare. Try this one out. Alright, in this problem we have three different pieces of our function that are being affected. First of all, we have a plus 2. This moves our graph up 2 from the parent function. We also have this plus 3 on the inside, which means that we're shifting left or right. And in this case, it's a plus 3, which is backwards from what we'd expect, which means that we've gone left 3. Finally, we have this negative on the outside, so this is representing a reflection over the x-axis. So now that we're able to look at a new equation and identify the transformations that have been applied from the parent function, now we're going to do the opposite of that. So I'm going to give you a parent function, or a function to start with. I'm going to give you some transformations, and you're going to write me the new equation of our function. So in this case, we're starting with our parent function, f of x equals x squared, and we want to apply each transformation in order. So first we're going to apply a vertical stretch by a factor of 2. Using our rules, I know that that means I'm taking 2 times f of x. So I'm using this rule, 2 times f of x. Well, f of x, remember, is just x squared in this case. So I'm taking 2 times my function x squared. And simplifying that, that's just 2x squared. Next, I'm going to apply a reflection in the x-axis. And that rule is negative f of x. So now I'm taking a negative times my function. But wait a second, my function is not x squared anymore. Now my function is 2x squared. So I'm taking a negative times 2x squared. And when I simplify that, I get negative 2x squared. Next, I'm doing a translation 3 units down. That rule is f of x minus 3. So I'm taking my function minus 3. But wait a minute, my function is not my parent function anymore. Now my function is negative 2x squared. So I'm taking that function and I'm subtracting 3 from it. So simplifying this, I get negative 2x squared minus 3. So this new equation, g of x, which represents these three transformations being applied to my parent function, gives me negative 2x squared minus 3. Alright, try this one out. So once again, we're starting with f of x equals x squared, our parent function, and we're going to start by applying a vertical shrink by a factor of 1/2. So we're using this rule 1/2 times f of x. In other words, I'm taking 1/2 times my function. And my function at this point is just x squared. When I simplify that, I get 1/2 x squared. Next, I'm applying a translation 2 units up. That's going to be f of x plus 2. But f of x is not x squared anymore. So if I take f of x plus 2, instead of putting x squared in here, I'm going to put my current function, which is 1/2 x squared. And when I simplify that, I get 1/2 x squared plus 2. So my new function g, which represents a vertical shrink by a half and a shift up 2, is 1/2 x squared plus 2. Alright, try this one out. Remember, you want to do each transformation in order. So we're starting with f of x equals x squared. The first thing I'm going to apply is a vertical stretch by a factor of 4. So I'm taking 4 times f of x. In other words, I'm taking 4 times my function, which in this case is x squared. And if I simplify that, I get 4x squared. Next, I'm going to apply a reflection in the y-axis. That's my rule of f of negative x. So that means that I'm changing my input value. So I'm going to be replacing my x, or my input, with a negative x. But I'm not doing it in my original function, I'm doing it in my most recent function. So I have my 4 and my squared value, but instead of putting an x in here, I'm going to replace that with my new input value of negative x. Now, to simplify this, remember that we do order of operations, which is parentheses, exponents, multiplication, division, addition, subtraction. So within these parentheses, I would do my exponent first, and if I take a negative x and I square it, it actually becomes a positive x squared. So the simplified version of this is just 4x squared. So really, that reflection over the y-axis didn't really do anything. So you can just leave it like this, or you can simplify it and give me this answer. Either one's fine. Next, I'm doing a translation 2 units up. So I'm taking f of x plus 2. So that means that we're taking our entire function and we're adding 2 to it. So at this point, our entire function is this 4x squared. So I'm going to put 4x squared in here in my parentheses plus 2. When I simplify this, I just have 4x squared plus 2. So after all three of these transformations have been applied, my final equation is g of x equals 4x squared plus 2. Alright, try this one out. So once again, we're starting with our parent function, f of x equals x squared. The first transformation we're going to apply is a vertical shrink by a factor of 1/3. So I have 1/3 times f of x. That means I'm taking 1/3 times my original function, which in this case is x squared. If I simplify that, I just have 1/3 x squared. Next, I'm going to apply a reflection in the y-axis. So that rule is f of negative x. In this case, I'm replacing my input value with a negative x. So I'm taking my function from before, 1/3 x squared, but instead of putting an x in there, I'm just going to put a blank set of parentheses, and I'm going to replace that x value with negative x. So once again, I can simplify this if I want, or you can just leave it. And if I simplify it, when I take a negative x and I square it, I get a positive x, which means that really I'm just back to this 1/3 x squared. Next, I want to apply a translation 3 units right. So that's going to be f of x minus 3. And once again, I'm changing that input value. So I'm just going to take a minute to show you that you could have a couple of different answers here depending on whether you simplified the last step or not. So let's say that I'm working off of this non-simplified version of that last function. I'm going to write exactly what I had before, but instead of putting that x value there, I'm going to replace that x value with x minus 3. So you'll notice in this case, this negative here is going to get distributed to each term, and I'll end up with negative x plus 3 inside of my squared term. Okay, so that's one possible way that you could do this problem. If you did simplify, then we're just going to start with our 1/3 x squared, and I'm just going to replace that x with x minus 3. So both of these are correct answers to this problem. They're both the same function, just different ways of writing the same thing. All right, try this one out. So once again, we're starting with our parent function, f of x equals x squared. The first rule that we're going to apply is a horizontal stretch by a factor of 2. So that means I'm using f of 1/2 x. Remember that with horizontal stretches and shrinks, we do the reciprocal of the description. So that means that I'm replacing my input value, or my x value, with 1/2 x. So I'm going to write my equation from before, but instead of having an x, I'm going to plug in a 1/2 x. So we could simplify this. I know that if I take 1/2 x and I square it, I can get 1/4 x squared, because 1/2 times 1/2 is 1/4. Okay, and you could leave it unsimplified, or you could simplify it. Either way, it's still correct. Next, we're going to apply a translation 2 units up. So that's f of x plus 2. So I could either apply that to my unsimplified version, which would mean I'd have this 1/2 x squared plus 2, or I could apply it to my simplified version, meaning I'd have 1/4 x squared plus 2. Either one is correct. Finally, I'm going to apply this reflection in the y-axis. So that is f of negative x. So once again, that's affecting my input value. If I take a look at my unsimplified version, I am going to just rewrite what I have exactly the way I have it, but instead of putting an x here, I'm going to put a set of parentheses with a negative x in it. And if I simplify that, I'm just going to multiply these two pieces together, so I have negative 1/2 x squared plus 2. Okay, so that is one correct answer. Now let's say that instead I was using my simplified version. I'd have 1/4, and instead of putting an x squared, I'm just putting a blank set of parentheses squared with my plus 2. And inside where x was, I'm going to replace that with negative x. And in this case, if I simplify this further, remember that when we take that negative x and we square it, it becomes a positive x. So this is really just 1/4 x squared plus 2. So this is also a correct answer. All right, try this one out. So we're starting with f of x equals x squared, our parent function again. We're going to start by applying a horizontal shrink by a factor of 1/2. That's f of 2x, because remember, with horizontal stretches and shrinks, we do the reciprocal of our description. So that means that I'm replacing my input, or replacing my x, with 2x in my original problem. So I'm going to rewrite my original problem, but instead of an x, I'm putting in a blank set of parentheses. And inside of that blank set of parentheses, I can put a 2x. We can just leave it like that and continue on, or you could simplify it. We know 2 squared is 4, so this would be 4x squared. Next, I'm applying a translation 1 unit down. So that's f of x minus 1. So using my unsimplified version, I'm going to have parentheses 2x squared minus 1, or I could use my simplified version and I'll have 4x squared minus 1. Either way, we get an appropriate answer. Finally, I'm going to apply my reflection in the x-axis. So in this case, I'm taking a negative times f of x. That means I'm taking a negative times my entire function. So if I take a negative times my entire function in my unsimplified version, I'm going to replace this blank set of parentheses here with my entire function. And I can distribute this negative to each term, which will give me negative parentheses 2x squared plus 1. So this is one of the appropriate answers for this problem. Now let's say that instead I was applying my negative f of x to my simplified version. I have negative times my entire function, or negative 4x squared minus 1. And in this case, I'm also distributing this negative through, which gives me negative 4x squared plus 1. So that is also an appropriate answer for this problem. Next, we're going to take a look at some of the advanced problems. So in the advanced concept for this standard, we're specifically looking at problems where we have multiple transformations that are affecting our input. So it might be a shift left and right followed by a horizontal shrink, or it might be a reflection in the y-axis followed by a shift to the left. Anytime where we're doing multiple transformations that affect our input values, it's going to be a little bit more advanced. So let's take a look at this example. We're starting with our parent function, f of x equals x squared, and I'm going to start by applying a shift down 4. So I have f of x minus 4. That means I'm taking my function from before minus 4. In other words, I'm going to end up with x squared minus 4. Next, I'm applying a reflection in the x-axis. So reflection in the x-axis, that's negative f of x. So that means I'm taking a negative times my entire function, which in this case is x squared minus 4. When I distribute that negative through, I get negative x squared plus 4. Finally, I'm applying a vertical stretch by 2, which is 2 times f of x. So I'm taking 2 times my entire function, which at this point is negative x squared plus 4. When I distribute that 2 throughout my function, I get negative 2x squared plus 8. So this isn't actually an advanced problem, but it is a harder proficient level problem where I have multiple transformations that are affecting my output values, and they're actually stacking on top of each other, and I need to make sure that I'm distributing and simplifying as I go. Alright, this is also a little bit harder proficient level problem, so give this one a try. Once again, we're starting with f of x equals x squared, and the first transformation I'm going to apply is a vertical stretch by 2. So that's 2 times f of x, or 2 times my function that I just had, which is really just 2x squared. Next, I'm going to apply a reflection in the x-axis, which is negative f of x. So I'm taking a negative times my function, which in this case is 2x squared. When I simplify that, I just get negative 2x squared. Next, I'm applying a shift down 4, so I'm taking f of x minus 4. So I'm taking the function I just had minus 4. In other words, I'm taking negative 2x squared minus 4. And when I simplify that, I just get g of x equals negative 2x squared minus 4. So you'll notice that in this last problem, when I did my shift down 4 first, and then I did a reflection or a vertical stretch where I'm multiplying by something, I had to distribute my negative or my vertical stretch factor through. But in this problem, when I did my vertical stretch or reflection first, so I did my multiplication part first, I didn't end up having to distribute anything through. So basically the order matters, and if we do a shift up or down before we do a vertical stretch or shrink or a reflection over the x-axis, then our vertical stretch or shrink will affect our shift. But if I do my vertical stretch or shrink or reflection first, then my vertical stretch or shrink will not affect my shift. Okay, now this one is definitely an advanced problem. We're looking at a horizontal stretch followed by a shift right 4. So these are two transformations that affect the input values in my function. So I'm starting with f of x equals x squared, and first I'm going to apply a horizontal stretch by 2, which is f of 1/2 x. Remember, we do the reciprocal. So I'm replacing my x with 1/2 x. And I could take that a step further and simplify that to get 1/4 x squared, but we don't have to. So next, I'm doing a shift right 4. If I do my shift right 4, I have f of x minus 4. So in this case, remember, I'm affecting my input value, or my x value. So if I take my function from before, and I'm just writing it exactly how it is, but instead of this x here, I'm going to put a blank set of parentheses, and in that blank set of parentheses, I'm going to put in my new input value, x minus 4. So now I can see that I'm actually going to have to be distributing this 1/2 through this set of parentheses. So I have 1/2 x minus 2 squared. So my new equation is 1/2 x minus 2 squared. Now if you simplified it, you could instead just have 1/4 x minus 4 squared. Either one is correct. Now let's take a look at if we do our shift left 4 first. So once again, I'm starting with f of x equals x squared. This time, I'm doing a shift left 4 first. So that's f of x plus 4. That means I'm replacing my input value, or my x value, with x plus 4. Next, I'm going to do my horizontal stretch by 2. So that's f of 1/2 x. So once again, I'm changing that input value, but I'm changing it in my most current function. So I'm going to write my function as is, but instead of putting an x in parentheses, I'm going to put in a 1/2 x. And then I simplify, and that's just going to give me 1/2 x plus 4 squared. So this equation is g of x equals 1/2 x plus 4 squared. So comparing these two problems, we can see that when you're looking at horizontal stretches and shrinks and how they're affected by horizontal shifts, if I do a shift left or right first, and then I do a horizontal stretch or shrink or a reflection over the y-axis, my stretch or shrink will not affect my shift. However, if I do the horizontal stretch or shrink or reflection over the y-axis first, anytime where I'm multiplying my input value by a number, and then I do a shift left or right, then I will be affecting that shift. So see how my shift here has changed from 4 to 2? So anytime that I do that horizontal stretch or shrink or that reflection first, it's going to affect your shift afterwards.